Hi there. Our world is filled with amazing nature that can be surprisingly well described using mathematics. And communicating that knowledge through education is how we preserve and develop our understanding of life. Unfortunately, we are often unaware that what we write is different than what we truly want to convey. There are times when a student loses points on his test just because the teacher misunderstood his work. In another case, what the teacher writes on the board or screen is sometimes incomprehensible to the students. In this video, we will discuss some basic ideas on how to write mathematical expressions in a more elegant, easy to consume way for readers, so that we can avoid miscommunication and deliver our message precisely. Please note that these tips do not have to be followed exactly. They are simply basic guides to better writing that are suitable for almost anyone who uses math in everyday life. Let's start with the underlying characters that live in math. The number 1 has many friends that look similar to it. One of them is the number 7. To avoid confusion, we can put some shoes for 1, or maybe it's just better to cross the 7 at all times. And then there's letter I. Always put bars to the uppercase 1 and a tiny dot for the lowercase 1. We also have the lowercase l. We can always change it into cursive form to distinguish it from the others. Next, the number 2 may look like the Greek letter alpha, and probably the number 3. To fix this, we can remove the loop on 2 and make 3 a little bit sharper on top. Problem is, though, it looks like the letter Z now. Luckily, it's enough to just cross the Z to make it different from the rest. Moving on, it's pretty challenging to tell these guys apart. Let's clarify things up by opening the top of number 4 and giving number 9 a tail. Now, this 9 might look exactly like the lowercase g, but no worries. Just pull a loop on g and the problem is solved. This applies to lowercase y as well. Keep in mind that it might be best not to make a loop on q, because otherwise it'll look like number 8 or perhaps the Greek beta. Now number 5. To avoid confusion with the letter S, give it a sharp crown. And then there's number 6 along with the uppercase C and G. Just make sure to close the 6 properly and give a pointy end for G. The last digit is the trickiest. One thing we can do to make 0 and the letter O distinguishable is to put some hair on O. And never pull lines on 0 or else they'll be a completely different guy. Adding just a small stroke will result in the letter Q. Horizontal slash is for theta, diagonal slash for empty set symbol, and a vertical slash for phi. There are also several other letters worth mentioning. Observe the subtle difference between the $U, the pointier phi, and the curvier nu. The sharper P and the smoother rho, the jagged W and the rounded omega, and lastly, the nasals like N, eta, M, and mu. Let's move on to how we get our friends to work with some basic operations. The addition symbol plus sign doesn't make any problem in most cases, except maybe with the lowercase t and the dagger symbol. Just make sure each stroke on plus is equally long, unlike a dagger symbol, and give t just a tiny tail. The subtraction symbol minus sign is used for, well, subtraction, but also to signify negative numbers. Just make sure it's not wavy like the tilde sign, not too short and not too long, and keep it in the middle of the line, unlike the underscore symbol. Now comes the trickier part. The multiplication symbol, times sign, is often confused with the letter X. Some people fix this by writing a cursive, fancy form of X. But this might be a problem, since it is sometimes mistaken as H, K, LE, or even DL. So another solution is to keep writing X as a normal cross, or clear a curve and change the times sign into a dot. Keep in mind that the dot for multiplication is in the middle, unlike a period. At the end of the day, the choice is really up to us, as long as we can't tell which one is which. Next, the division symbol, obelus sign, is a rare creature. As the symbol suggests, it really just represents a mini fraction symbol, encouraging us to write division as a fraction or using a slash like this. Just remember to draw the fraction bar as long as necessary until it covers all the dividend and the divisors, and keep it as steady as possible. Using fractions instead of obelus sign is much more convenient when we have longer expressions. For the nth root notation, we often use this radical symbol. The number n above the radical is called the degree or index, and whatever lies under the radical is called the radicand. Just make sure the index is written smaller and stays above the middle line so that it's not mistaken as some constant multiplier on the left, and keep all the radicand stays under the roof of the radical sign. For the exponentiation, the exponent works the same way as the index of an nth root. Keep it above the middle line of the expression, making it higher than the base. And lastly, for the logarithm, write the base under the middle line of the expression. Additionally, to make it much clearer, we can put some parentheses between the anti-logarithm. After we have our digits, letters, and some operations, we can start creating our mathematical expression. Basically, an expression is a family of those symbols combined together, like this, or a more complex one like this, or even as simple as this. But don't worry about what they mean now. We just want to grab the idea of what a mathematical expression looks like. When we have two expressions, and say they are of the same size or value, we basically have an equality. And we use an equal sign to indicate our equal friends. If two expressions are not equal to each other, we simply have an inequality, indicated by some other symbols. Now, when we derive some math expression using equality or inequality, there are two types of writing. The inline style, where we write the whole expression on the same line continuously writing a normal sentence, is good for saving spaces, but it's totally not pleasing to be read by someone. Why? Because reading a train of math without stopping makes the information harder to swallow, and the readers are more likely to miss something along the way, forcing them to reread it too many times, and making them give up learning at the end. Another way is to use the array style, where we put each derived expression in a different row. We write each expression on a new line every time we meet the equal or inequality signs, so that each row starts with those signs. Just make sure that they are lined up to give a tidiness feeling for the readers. This style will probably take up a lot of space, but the thing is, sometimes having an information delivered effectively and appealingly is more gratifying than saving spaces on the paper for nothing. To sum up, the inline style can save space, but the reader will more likely have a hard time dealing with the information, so it is suitable for shorter expressions. On the other hand, the array style is easy to follow by the reader, but it takes more space, so it is good for writing longer expressions. Let's also talk about one gear that a math expression could have. A single expression may have some smaller sub-expressions indicated by the brackets surrounding them from left and right. When we write some complex expression where we want to group the order of the evaluation, we may use several brackets. In other words, we can form a nesting where a sub-expression may have sub-sub-expressions and so on. The innermost group expression is evaluated first before the outer level right outside this expression, and it continues up until the outermost group. The problem is, sometimes it's hard to identify which group is the innermost level among all the sub-expressions, and it becomes exponentially harder the more the brackets are used. This is where various types of brackets step in. There are 4 frequently used bracket forms: round brackets or parentheses, square brackets or simply brackets, curly brackets or braces, and angle brackets or chevrons. Let's see our new friends in action. Start with an expression. If we have one level of group sub-expressions, use parentheses to isolate them. For the second level, use square brackets for the outermost layer. For the third one, we have braces. And if there is a fourth layer, use chevrons. Having 4 or more levels of nesting is quite rare, but not impossible. Now we might ask, how about an expression with more than 4 layers? Well, the clever way is to simply repeat the cycle. So basically, the 5th layer uses parentheses as with the first, 6 uses brackets as with the second, and so on and so forth. By using a cycle of 3 or 4 bracket types, we can effortlessly count how many layers are there in an expression. I mean, just imagine all these brackets are written in just parentheses alone. It's true that it might seem consistent and perhaps neater for some people. But on the other hand, it takes a lot more time to figure out which level is which. If we take a look at glued brackets like this, it can easily lead to confusion, especially for readers who happen to read it for the first time. So if this convention sounds a lot more helpful, anyone is definitely welcome to put that brackets family into use. And remember, don't ever be lazy to use brackets whenever it needs to. Finally, we should consider one of the most underestimated math operations of all time. Let's say we have this fraction. We can break down the numbers in the numerator above the line and the denominator below the line into smaller objects. So let's write 12 as 2 times 6 and 30 as 5 times 6. This is called a factorization. Now we can divide both numerator and denominator by 6, leaving us with our new friend 2 over 5. This whole process can be boiled down to just removing the common factor 6 of both number and we have the simplified expression. Now let's keep that aside and consider this expression. If we look carefully, we can see a positive 4y and a negative 4y appearing together. We can work on them to get 0, but this doesn't add anything up to the original expression, so we can just remove it. We can do it with one step by just crossing them, since we know they add up to 0, and we're left with x plus 1. Let's take a look at one more example. We might be tempted to cross out b plus c in this equality, leaving us with a equals d, but we have to be very careful, because this is the same as dividing both sides by b plus c, but we can never divide by 0. So we have to take into account that b plus c is not 0. Once we clear things up, we can go ahead and make a conclusion about it. Now think about this. What is the underlying idea that all these examples share? Well, notice that this simplification process does not change the value of the original expression. It only makes things simpler and shorter. These guys are equivalent to these simplified guys respectively. This is the idea behind cancelling out. However, this simple idea sometimes may confuse someone who happens to read it for the first time. Just imagine if we encounter this complex expression in the wild and after cancellation, we ended up with this. We might need more time to clarify whether the result is true, or even worse, we might have no idea at all how it gets to the next step. So to write better, we have some options. Anyone might have noticed how each of these cancellations is written using different cancelling styles. The first option of cancelling is a creative cancelling, which is basically a cancelling by crossing different terms using different symbols. As an example, let's use the previous expression. We can use a single stroke for fraction cancelling, and then change the direction for the other. Oh, and if the term is not cancelled to 1, draw some arrow and write the result of the division along the direction of the arrow to keep track of what's going on. In this case, 10 divided by 2 is 5. If we run out of direction, we can use double strokes, or change thickness, or even change the curvature of the line. So just let our creativity do the work. When the term reduces to 0, we can draw a cross on them to show that these terms really vanish. If this sounds a bit too handful, and we happen to have a colored pen, colorful cancelling is another way to go. Colorful cancelling is a cancelling by crossing different terms using different colored pens or markers. So for example, use red first, and then blue, then green, and so on. Notice that this enables us to use the same stroke symbol for all the terms, and how different colors incredibly help us keep track of the cancellation process. Both cancelling styles have their own charms, and are suitable for people with various backgrounds. I mean, for instance, the colorblind people can use creative cancelling instead of colored one, right? So to recap everything, we have discussed 5 basic advice on how to write mathematical expressions. We talked about writing digits and letters, arithmetic operations, equality and inequality, brackets, and how cancelling out works. If anyone finds this to be helpful, feel free to apply them on notes, papers, or even blackboards for the sake of fellow readers. Since there are things that cannot be covered in this video, we will discuss more next time. Math is hard, but it can be made exciting if done right, and it starts with enjoyable writing. Thanks for watching.